For the last week and a half, we have been working with different situations of gain and loss of heat and calculating how much heat is gained or lost in those situations. Another thing that we have to consider is that when something is heated or cool, it actually changes in size. On Friday, you saw an example of something changing length. You were working with what's called a bimetallic strip. And on one side of the strip is one type of metal, and on the other side is a second type of metal. And when you started heating that metal started to curve because one type of metal had a better ability to expand as it was heated. This is actually what is known in a circuit breaker. Those of you who are in basically, what happens when you trip the circuit, imagine these are the wires going to the house, here. If you have too many things plugged in at one time, and there's too much energy running through the bimetallic strip, it starts to heat up, and it starts to bend, and it will disengage the circuit. It's actually a safety feature. However, in the older homes, they generally give each bedroom its own circuit. They put many bedrooms on circuits, so as soon as somebody starts to use the computer and then blow dry their hair and who knows what else, I know my house is going to the circuits. So the freezer gets its own dedicated circuit because when the circuit breaker trips on the freezer, that's not we also have a change in volume. So you saw that with the ring that you had to heat up so the ball could go through the ring. Thank you so much to whoever stuck the ball inside of the ring and got it stuck. So appreciate that. Thank you, Coleman. So things will actually change in three-dimensional shape. We see this with water when it freezes. I mean, you do probably have the experience of breaking a water container open because you left it in the freezer and it was too full. So we learn pretty quick about those things. This concept has a lot of connections to the real world. So you may have heard of trains derailing, especially on hot days. If there are not gaps left between the rails at certain points of time, when that rail heats up, it will actually start to expand and distort the track. So here, this is a distortion in length. Here, right there. And it's hard to see at this one, but right in here, you'll see a little bit of a wave. When the train hits up, it can derail. We see this issue with bridges as well. We have to make sure that we have expansion joints in our bridges to make sure that as the steel structure expands and contracts, it has a place to expand to without our bridges warping and losing structural integrity. So linear expansion. Most objects, when heated, will expand. Why? If I could zoom in, what would that be to show me why this happens?
Particles moving.
Okay, so we do have particles. Everything is made up of particles. Goes back to that particle theory here. So if you imagine a bar of steel, for example, made up of thousands of metals and millions of particles, okay, those particles start to heat up. What happens to motion? They vibrate more. Okay, so they don't just move, they move faster. And if you start moving faster, you bump up against your neighbor a little bit more. You take more space. the more the particles gain more energy, move faster, and spread out, which is why the whole object will expand.
Sky, you get real.
She still never said no. She still never said no. She did.
When we talk about linear expansion, we are talking about object expanding on either ends. We're not talking about the volume or everywhere surface area there is expands, just on the front end and the back end, particularly for when we're planning on building structures. Linear expansion is really important to us. Solids can expand in every direction. But when we talk about linear expansion, we're limiting our investigation to a single direction. Linear expansion, change in length, depends on three things: change in temperature, original length, and the substance. Why do you think that linear expansion depends on change in temperature?
Because basically everything expands when it gets hotter.
Okay, so let's say we have a minus 40 day, and 2 days later we have a minus.
And when it gets colder, it shrinks.
Honestly, I think this is probably one of the worst years for the profession comes in to cut back on things like structure supports after the winter that we've had. We've had huge fluctuations in temperature throughout the winter season, and as a result, our highways are in pretty bad shape.
I live that way. I take the grids. I take the grids.
But it's bad. When you live long enough,
Yeah.
It's there's a section of street from this where the first street from Glasgow's to Midtown. It's almost like a whole line of potholes.
Norland's really bad too. Just where the tires are, yeah, this long yeah.
But the reason why it's so bad is because of this constant change in temperature. Not little changes, but huge changes in temperature. Changing by 40 degrees in a day or two, that is quite a fast shift. And that's hard because things will grow and expand constantly. But they're shifting by a lot. Why do you think the original length of the object matters to how long it can expand to? Yes.
I can take it.
Please take it. I wasn't able to push it back in front of it.
Okay.
Why do you think the original length matters?
So that you know the final difference.
Okay. Let me give you an example. Suppose we have a section of track that is 1 meter versus a section of track that is 10 meters. Do you think that's going to make a difference?
Pardon?
Do you think it's going to make a difference in how the railroad track section that's 1 meter versus 10 meters long?
Like of how much you can expand?
Oh no, the ratio's gonna be the same.
That whole 10 meter section expands, not just the 1 meter section. So the longer it is, the more expansion you have to deal with. That's why railroad ties are a certain length long. The substance matters. Why do you think the substance matters?
Because they have different expansion points, different temperatures.
Why?
Because they're different densities.
What makes them different?
Particle density.
So if you look at the base, what they're made up of, particles, they're different.
You got it
Now,
right.
thankfully, somebody's done the hard work. Let her find out these numbers are. What you have to do is be really careful about what column you use. Because one column is for linear expansion, one column is for volumetric expansion. Notice that all substances in the linear expansion are solids. When you start bringing in volumetric expansion, you start considering elements such as gasoline. Here is the formula. Similar to our Q equals MC delta T formula, we have 4 things that we need to keep track of in order to identify what it is we're solving for. Question 1 says, a 1.00 times 10 to the 4 meter scale railroad track with a coefficient of linear expansion of 12 times 10 to the negative 6 degrees Celsius changes temperature from 18 degrees Celsius to 38 degrees Celsius. It wants to know how much that track is going to expand by. The hardest part is putting the variable with the number. So if we say 1.00 times 10 to the 4 meters, where does that belong?
What, the decimal?
This is the original length.
The A.
How long is that? 1.00 times 10 to the 4.
1,000 meters?
Pardon? 10 meters?
No.
10,000 meters.
It's 10,000 meters, which is how many kilometers? Would it make sense that a piece of railroad track is going to be the length of here to Sturgis?
No.
No. And I'll show you in a moment why that is such a ridiculously long length in railroad track. Coefficient of linear expansion of 12 times 10 to the negative 6, that's the A symbol. That's either going to be stated right in the problem, or you're going to have to look at this data table. Okay, but generally, A comes from a data table. You're not usually calculating A. So 12 times 10 to the negative 6 per degrees Celsius. It says that the steel track changes temperature from 18 degrees Celsius to 30 degrees Celsius. So this is basically a hot summer day.
Midsummer Night's Dream?
What is the change in temperature? What is the change in temperature of number 1?
Change in temperature is 20 degrees Celsius.
20 degrees? Is it going up 20 degrees or is it going down 20 degrees? Up. Okay. So what we're trying to do is find out how much that steel track is going to expand. Change in length is going to be equal to the original length times coefficient times delta t.
Why are we dividing the A by degrees Celsius? Why are we dividing degrees Celsius?
That is actually the unit of measurement for A. It's something per degree Celsius. It's a really, really strange unit. Essentially what that's going to allow us to do is to calculate, or sort of cancel out degrees Celsius and delta T. I'll show you in a moment. That is your equation. So change in length is going to be 1.00 times 10 exponent 4 meters times 12 times 10 exponent negative 6 over degrees Celsius times 20 degrees Celsius. You see what having the units of over degrees Celsius is going to allow us to do now? Degrees Celsius divided by degrees Celsius is equal to 1, which means we're going to collect meters as the answer. Now comes time for some number.
But it's all
Good review of how to punch in exponents to your calculator. Remember?
Yep.
Make sure you use the E button or the EX button when you're doing this.
it's 6 weeks. I want 6 only 1 minute. I don't know if it's
Miss Patterson, it's delta L over 1 times 10 to the power of 4 meters, or is that just an arrow under the meters there?
So what I'm using the arrow to is to indicate that the units left over is units.
Oh, okay. I didn't see that there. I thought it was
Oh,
like
sorry.
meters over something.
I don't know my name.
Federal got 2.4.
I don't want to.
Look at under the question. I have to play.
I feel like I'll actually try this one.
I just.
Okay. So, what kind of an answer did you get?
By that I mean 2.4
You
meters.
just listen at the answer.
No, I
240 centimeters.
Alright, so that means that steel track is changing by length on that day from the start of this coffee cup to right there. You want your track changing by 2.4 centimeters on a hot day. That means that your track is going to be 2.4 meters longer, which means it's going to curve out.
That's why there's little gaps in here.
That and short sections. There's gaps because each one of those steel rail tiles is actually its own rail tile. That one, because it's a shorter piece, is not going to turn by this much. You would have to really some good pinching. So, question for you. What would be an acceptable length change for
Don't have the
6,000 million.
what do you think would be an acceptable length change?
Foot.
12 meters?
12 inches.
12 inches, which is 24. Let's say 25 centimeters. So we need to use metric units. Okay. So you're saying that it's okay if your steel track changes by this much.
How big are the wheels? I don't know why they're called trains. What happened?
I've never had anybody ask me that.
Is there a big difference because the wheels are large, then they wouldn't notice the.
It's not getting wider.
Yeah, I know, but if they're smaller wheels, then they could go around the curve easier. Do you understand at all what I'm saying?
Huh.
I'm just gonna stop dating myself a little bit.
They're like, wow.
Huh.
Yeah, cool.
Okay, let's see if we.
I'll get a picture of it.
So that doesn't make sense.
Gonna send it.
Oh, that says 37 millimeters, which is 3 centimeters. That makes no sense.
They're on cold Snapchats.
Still gonna send it.
What about this? The tread is 2.5 millimeters approximately. That doesn't make sense. I'm not using.
Steam engine, but they made of water then.
Alright, let's see if we can look here. Okay, I'm gonna turn this off.